taken from the November 2015 grade 12. 2 blocks of mass m kilograms and 2.5 kilograms are connected by a light inextensible string. The string runs over a light frictionless pulley as shown in the diagram below. The blocks are stationary. 2.1.1 State Newton's third law in words. When body A exerts a force on body B will exert a force of equal magnitude but opposite direction on body A. 2.1.2 Calculate the tension in the string. Let's draw a free body diagram for the m kilogram block. There will be a normal force there because the block is lying on a flat horizontal surface. And then this is the force of weight. So the blocks are not moving. So this is the static friction. And then we have force of tension to the right. This is for the m kilogram. And then the other block is hanging. We will have a force of weight acting downwards and then a force of tension. This is for the 2.5 kilogram. We don't have the mass of this block, so it will be hard to find the tension using the m kilogram block. So let's use the other block. Sum of the forces that are acting on the y component is equal to mass times acceleration in the y component. We have a force of weight that's acting downwards, and then tension is acting in the opposite direction. For forces that are going in the same direction, you add them, and forces going in the opposite direction, you subtract. This is force of tension. We do not have acceleration because the blocks are stationary, so this is equal to 0. The weight is mass multiplied by gravitational acceleration. This should be equal to the force of tension. Force of tension is 2.5 multiplied by 9.8. So this is 24.5 newtons. 2.1.3. The coefficient of static friction between the unknown mass m and the surface of the table is 0.2. We are given as 0.2. So they want us to calculate the minimum value of m that will prevent the blocks from moving. Let's start with the m kilogram block. We have some of the forces that are acting in the y component. This is MAY. So in the y component, we have the normal force minus the force of weight. This is a subtraction sign because they are going in opposite directions. And then there's no movement, so the acceleration is 0. The normal force should be equal to mass multiplied by g. 9.8 multiplied by m. We don't know what the mass of the block is. Now I'm going to focus on the forces that are acting on the x component. We have force of tension to the right, and then we have force of static friction to the left. Still, there's no movement, so this is equal to 0. F of s is equal to us multiplied by the normal force. You have this equation in your data sheet. The force of tension, we calculated that the tension there was 24.5, and since the 2 blocks are connected by that string, it means that the force of tension should be equal to 24.5 as well. So this is US, and US we are given as 0.2. And then the normal force, we have it as 9.8 multiplied by m. This is 9.8 multiplied by m, which is equals to 0. 24.5 is equals to 0.2 multiplied by 9.8. Therefore, the mass of the block is 24.5 divided by 1.96. This is 12.5 kilograms. 2.1.4. The block of unknown mass is now replaced with the block of 5 kilograms. So now we have M1 as 5 kilograms. The 2.5 kilogram block now accelerates downwards. So now we have acceleration. And this M2 is equals to 2.5 kilograms. The coefficient of kinetic friction between the 5 kilogram and the surface is, so we are given UK as 0.15. Okay, and they want us to calculate the magnitude of the acceleration of the 5 kilogram block. The force of tension as well as the acceleration will be equal in magnitude for both the blocks, because whenever this block moves, this one will move at the same speed as well, or at the same acceleration as well, and the tension will be the same. The sum of the forces that are acting on the x component should be equals to MAX. Nothing has been changed, all the forces remain the same. The only thing that they've added now is the acceleration. We will have force of tension minus force of kinetic friction, which is equals to the mass multiplied by the acceleration. The force of tension we do not know, but we do know that Fk should be equals to mu k multiplied by the normal force. The normal force is just mass multiplied by the gravitational acceleration. So we're just going to substitute. This is 0.15 multiplied by the mass is a 5 multiplied by 9.8, which is equals to 5e. So force of tension is equals to 0.15 multiplied by 5 multiplied by 9.8. This is 7.35 plus 5e. This is equation 1. Some of the forces that are acting on the y component, because we do not have any movement in the horizontal component, only vertically. The blocks are sliding down, so the force of weight should be minus the force of tension, mass and acceleration. The force of weight, that's mg, so the mass is 2.5 multiplied by 9.8 minus force of tension. This is 2.5 multiplied by acceleration. The force of tension is equals to so this is 2.5 multiplied by 9.8, which is 24.5 minus 2.5a, and this is equation 2. The force of tension on the 5 kilogram is the same as force of tension on the 2.5 kilogram. So we can just equate the two. 3.5 plus 5a is equals to 24.5 minus 2.5a, and solve for the acceleration. 7.35 minus 24.5 minus 17.15, which is equals to minus 7.5a. This is 2.29 meters per second squared. 2.2. A small hypothetical planet X has a mass of, so this is the mass of the planet, 6.5 times 10 exponent of 20 kilograms, and a radius of 550 kilometers. This is 550 times 10 to exponent of 3 meters. Calculate the gravitational force of weight that planet X exerts on a 90 kilogram block on this planet's surface. The mass of rock is equals to 90 kilograms. Force is equals to G multiplied by the product of the masses over R squared. This is 6.67 times 10 to exponent of negative 11. M1, that's 6.5 times 10 to exponent of 20. M2, that's a 90. This is 500, it's 550 times 10 to exponent of 3 squared. 6.67 times 10 negative 11. 6.2 times 10 exponent of 20, and then 90 over 550 times 10 to exponent of 3 all squared. Minus 11, 6.5. Okay, yeah. So I'm getting 12.899. This is 13.0 newtons.